Here's a really interesting rigid body dynamics problem, which looks like it starts as an equilibrium problem, but then something happens and then things start moving. So let's read the question and let's see what it wants from us. So we're dealing with a square panel, which has the length of one side of B, and then the mass of the square panel is 12 kilograms. Now, this square panel is attached to point C with the aid of two wires, and then one of them just breaks, and we're asked to find the tension in the other wire. Now, if you'd like to see anything similar to this in the future on the channel, or if you have any suggestions for any specific problems that you'd like to see, let me know in the comments. Now, what I would do here is I would just draw a free body diagram. So I would draw my square like this, and then I would draw all the forces acting on the square. So the first thing we have, the obvious thing, is the weight, right? So that's going to be my mg, which is acting here. And the other thing I will have is just the tension in the cable AC, right? So I'm going to draw that like this. And I know this force is acting at a 45-degree angle because the cable is at a 45-degree angle with respect to the horizontal, right? So this angle here is 45 degrees. There's no tension in the other cable because it's broken. And those are all the forces that we are dealing with. So what I would do now is write Newton's second law, okay? But before that, I think it's worth thinking what's the coordinate system that we want to use. So I could use this kind of coordinate system, and the problem will be able to come to a successful conclusion eventually. But it's much easier actually if our coordinate system will be like this. Okay, so you'll see why that happens shortly. But essentially, my x and y axes. So my x-axis is going to be along the tension force, and the y-axis will be perpendicular to that. So this is my coordinate system of choice. So the other thing I'm going to do is I will write the equation of motion along the x and along the y-axis. And I'm going to call this point here O. Okay, so the first thing we have is that the sum of forces along the x direction will be equal to, and I'll write it like that. So the sum of forces along the x direction equals the mass of the square times ax, where ax is actually the acceleration of the center of mass in the x direction. So that's the acceleration of just this point over here. Okay, so let's try to see what forces are acting in the x direction. So first of all, we have tension. So tension is purely in the x direction. And the other thing we have is some component of the weight, right? So the weight has a component in the x direction, and we know this angle to be 45 degrees because it's the same as this angle. But this component of weight is in my negative x direction. So we'll have minus mg, and then we have cosine or sine of 45 degrees. It doesn't really matter because it's the same angle in both cases. The correct thing to write would be cosine, and that would be square root of 2 over 2, and that is the mass times ax. Okay, and the other thing I'll do is I'll write the equation of motion in the y direction. So along the y direction, what I have is only one component of weight, right? So there's nothing in terms of tension because tension is purely in the x direction. So if we look at what happens along the y direction, we only have this component of that blue arrow, which is, well, it's the same as this. And it's acting in the negative y direction, so it's minus mg root 2 over 2, and that's equal to the mass times the acceleration in the y direction of the center of mass. Okay, so the last thing to do is to write the sum of moments where counterclockwise is positive And the sum of moments about point O, that's going to be equal to the moment of inertia about O times the angular acceleration. Right. So about point O, there's no moment due to the weight because the weight is acting through point O. So the only thing we have is the tension, which is producing a clockwise moment, which means that we have minus T multiplied by the moment arm, and the moment arm should be b square root of 2 over 2. And you can actually check that, right? So the diagonal of the square is b root 2, and then you divide that by 2 to get the moment arm. And that equals this. Now, for a square, this is equal to 1 over 6, the mass of the square times the side squared, so times b squared, and then times alpha, which is the angular acceleration. So what we can then do, just to simplify this a bit more, we can cancel out the 2 on both sides, and then we can cancel out the b from both sides, and we just have that minus t root 2 equals 1 over 3 m b times alpha. Now, at this point, it looks like we have too many unknowns. So we have t, we have alpha, and then we also have those accelerations here. We have the ax and the ay. So we need one more thing. And we can actually use the fact that point A is attached via a wire to point C, right? And point C is not moving, point C is fixed, and you know that. Which means that at the beginning, when there's no angular velocity yet, then what this tells us is that the acceleration of point A, so I'll write that here, the acceleration of point A is going to be purely in the y direction. So the acceleration of point A at the beginning is going to be like this. So somehow along the y direction. Usually, if this cable here was moving, then there would be a normal component, sort of a centripetal acceleration pointing towards C. But this only happens if that cable has an angular velocity, which it doesn't, because we're looking only at the initial moment when the second cable breaks. So it's safe to say, therefore, that the acceleration of A is purely in the y direction. So it only has a y component, and this is how we can write that, right? Or we can also write that the acceleration of A in the x direction is equal to 0. And this is actually the key to be able to solve this problem. And let's see how we can do that. So I'm going to use Euler's formula for acceleration. So here's how we apply that. We say that the acceleration of point A, right? I'm going to apply Euler's formula between point O and A, right? So we have the acceleration of A is equal to the acceleration of O plus the angular acceleration that we don't know, and then cross product with OA. And normally we have that other term as well, right? But this term is 0 because, once again, we don't actually have an angular velocity when everything just starts moving. So the acceleration of A has only a y component, so I can write that as A times j. And then the acceleration of O has the two components that we were talking about earlier, so that's ax and ay plus, and then I've got my determinant, which involves my angular acceleration alpha, which I don't know if it's positive or negative, but I'll treat it as positive for now. And then OA is going to be equal to b root 2 over 2, and it's purely in the y direction, in the positive y direction even. So that's b root 2 over 2, and then this is 0. Okay, so let's see what happens if we solve this determinant. So we have on the right hand side axi plus ayj, and then the determinant is just going to have an I component that will be equal to minus alpha b root 2 over 2. Okay, So on the left-hand side, I only have a j component. So that means this is equal to this on one hand, and on the other hand, which is more important than that, is this and this are zero. Okay, because there's no x component on the left-hand side. So we have ax minus alpha b root 2 over 2 equals 0. So this actually gives us a nice relationship between ax and alpha. So we have ax equals alpha b root 2 over 2. Okay, so what we can do now is we can take ax, we can substitute it back into our previous equations, and we can find the formula for tension, which is what the question is asking us to find. So what I would do here is I would take this equation and I would substitute ax in it. So here's what we have. We've got tension minus mg, and then we have root 2 over 2 equals mass times ax. But ax we know is equal to this, so I'll just write that instead. So it's alpha, and then we have b root 2 over 2. And the other thing we have is this, which is minus t times root 2 equals 1/3 mb alpha. So 1/3 mb and alpha. And what I would do now is I would just make alpha the subject in the second equation, right? So alpha should become minus 3t root 2 divided by m times b. Okay. And now we take this and substitute in here. And we have t minus mg root 2 over 2 equals m. And then I have my b root 2 over 2. And then I will substitute alpha with what alpha is. So it's minus 3t root 2 over mb. Right, so here's what we have. The mb and the mb cancel out. Then we also have root 2 times root 2 is 2, divided by 2 is 1. So we have tension minus mg root 2 over 2 equals minus 3t. So this is the only thing we have left, right? Which means that if we move things around, we're going to get that 4t on this side equals mg root 2 over 2. And finally, the tension will be equal to mg root 2 over 8, which if you put the numbers in, you will just have that this is approximately equal, I think, to 20.8 newtons. And yeah, and that's how you find the tension. So what we did was we applied the Newton's second law along the x and the y directions. Then we did the same thing for rotation. And then we used this relationship, which connected the accelerations of points A and O, so the center of mass O, which is here, as well as point A, which is where the cable is attached. And when we used that, we were then able to find something which connected the acceleration of the center of mass and the angular acceleration of the square. And after a couple of substitutions, so this from this point onwards is just pure maths. And we were able to get the fact that the tension has this expression, which turns out to be something like this. And that's the end of the question.